All right, this is Solving Systems Day 2, and now we're just going to kind of move on from word problems and talk different techniques about how to solve different systems. So we're going to kind of move on to a two-variable two-equation system, which is what you were doing with the word problems, and now we're just going to talk about a bunch of different techniques. So this first one, we're going to try by substitution. And these are called linear systems because there's no powers on anything. If I solve these for y, I could graph them. They would just be lines. We're essentially just trying to figure out the solution that works for both systems at the same time. So I'm going to look at the equations. I'm just going to pick out the one that looks easier. This top one looks slightly easier. This y is kind of already by itself, so that's the one I'm going to focus in on. So I'm just going to take that equation off to the side. And the y variable looks the easiest because it has no coefficient with it. So that's who I'm going to solve for. It just requires one step of me. So that one's pretty easy. And then we're going to take that and we're going to plug it into the other equation. You don't want to solve and then re-plug back in to where you started. You'll end up, everything will go away. So make sure that you're plugging into the other equation. So I'm going to take 3x minus 2 and then I'm going to put my y value in there that I found. And now our job is just to solve this, which should be, hate to should you, but should be pretty easy. So here's 7x, add 4 to the other side, and we get 2 for x. And then we just have to plug that back in. This is usually, if you just kind of go back and forth, they're set up nice for you. So take that 2, plug it in right there, and 5 minus 2 times 2 just gives us a 1. So the solution to this system is 2, 1. And we write it like a point because what we're really looking for is where those two equations intersect each other. Trying the next one, that first equation looks like the easier one. It doesn't really matter which variable you say you're going to solve for because as soon as you move the y over, they actually are equal to each other. So I'm going to take 5x minus 3. Again, it doesn't matter which one of these you solve for because they're equal. So I'm just going to replace the y with an x. You could just as easily replace the x with the y and solve for y first. It doesn't matter. So 5x minus 3x gives me 2. Divide both sides by 2, I get 3. And since x and y are the exact same thing, the point here is 3, 3. So what we're really trying to do in a system of two equations with two unknowns, so that's like our x and y, two equations, you can have exactly one solution. They meet at a point. We just found that point. We did two examples where we found the place where they intersect. So you can have one solution that looks like that. You could actually have 0 solutions. Just means that your two lines are parallel. They're never going to touch. So that means they have the same slope. And if you run into that situation, the answer is literally 0. Like they will never touch. So, and we'll do one of those where you can see what that looks like. And then you can actually have what's called infinitely many solutions. And we usually just write IMS for infinitely many solutions. And what that means is this equation is actually on top of the other one. You just can't see it. So they're the same equation. They don't look like it right away, but they are the same equation and they're sitting on top of one another. So they hit at all of these points. So that means there's infinitely many times that these two lines hit. So it's called an infinitely many solution. So the solutions of the system are just places where the equations intersect. Mathematically, it's where they equal each other. So 2 more to go here. Oh, this one looks kind of worse. This one's got a fraction in it. That's kind of yuck. So I'm going to pick the first one instead. I'm just going to solve this for y. Doesn't really matter which one you pick. Actually, now that I'm looking at it, negative 3 minus 6x over 5. Also kind of an awkward, cumbersome thing to work with. We're going to have to work with that fraction. Might have been a little bit easier, I don't know, to do this one and solve for x so that you could kind of, then you'd have to plug that in there. I mean, you're going to end up working with a fraction no matter what. Just kind of depends on which route you take, but it truly doesn't matter which one of these you pick. Doesn't matter which variable you start with. Once you start on your path, then just remember to substitute into the opposite equation. So this is going to be negative x minus 5, 6. Then we're timesing by all of this, which does look like a bit much, but actually most of it's going to cancel, which is kind of convenient. So negative x and then minus. So what's going to happen each time is you're going to end up distributing this 5, 6 in. One job we can do before we get started is just kind of cancel off these 5s. I got one on the top, one on the bottom, so get rid of that. And then we've got a negative 1/6 and then negative 3 minus 6x. That's a little bit easier to look at. I don't have two fractions that I'm trying to combine, kind of just get rid of that 5 right away. Now I'll distribute this negative 1/6. So in that negative 1/6 times negative 3, we're actually going to get a half. So I got two negatives make a positive, and then 6 divided by 3 is a 2. These two negatives will make a positive, and then the 6 on the bottom and the 6 on top cancel, so you're left with just the x. And then I have negative x plus an x, so those kind of cancel out. And then I have 1/2 equals negative 7. Well, we know that that's not true. 1/2 is not the same as negative 7, so this system actually has no solution. It means they will never intersect. We ran into a situation where we got a false statement. 1/2 is not equal to negative 7, so that means that the system does not have a solution, that they are parallel to each other. And I'd actually find that out if I multiplied this by 6, negative 6, we'd match all the way through, and then that would also mean that these guys are canceling each other out. Like we're getting to a place where you're making a false statement. So anytime that happens, it just means you don't have any solutions. This one has got so many fractions on it. It's kind of terrible to look at. I don't want to start solving this and then having to multiply by the reciprocal of this. It gets a little cumbersome with the fractions. One way you can kind of eliminate that is multiplying by something that will get rid of the fractions. So I've got a divide by 4 and a divide by 4. So if I just multiply this row by 4, that will get rid of the over 4s. So if I multiply this by 4, the 4s will cancel. I'll have 3x. If I multiply this by 4, the 4s will cancel. I'll have a negative 1. And if I multiply this by 4, I'll have negative 4. And that is way easier to look at than how this started. I'm going to do the same thing down here. I got a 3 and a 3, so I'm going to multiply this row by 3. So 3 times x is 3x. And then when a 3 comes in here, the 3's will cancel, and I'll have a minus 1y. And when I multiply this by 3, 3's will cancel. I'll have negative 4. And then look at that. They are the same equation. So that means that they are sitting right on top of each other, this example. So we have infinitely many solutions. So that's kind of just your first day in terms of substitution, where you kind of solve one equation for one variable and then plug it back into the other.